Hello, welcome to another lesson of trig. Today we're learning about vectors. So suppose we start off with a small piece of candy like this, the kind of candy a kid would eat. And suppose we add to this piece of candy a very tall young kid, and we have this guy grabbing onto the candy and pulling it with all his might. He wants the candy. Now suppose we place another kid maybe here who also is interested in the candy, and this kid is pulling it this way. And you can even have maybe a little ant here, a tiny little ant, and this ant is trying to pull the candy this way. You get the point. The point is a lot of forces are trying to act on this candy. And if you look at these forces, there are two things that characterize each of them. Some of them pull this way, some of them pull that way, some of them pull this way. So right away, one of the things that characterizes these forces is the direction. Maybe we'll go right on here, direction. Each force has a different direction. The other thing that characterizes them is the amount of force. If you've got a big kid, that big kid could probably pull much harder than a little tiny ant. And so the size of it, this force is really, really huge, while this force is tiny force. And this one is medium. So the second thing that characterizes these forces is the size. Now this is how vectors were born. Vectors are things that represent two things, direction and size, or sometimes people say direction and magnitude. Exactly like these forces. Some of them are huge forces, other ones are smaller forces. They all point in different directions. That's what vectors are. So if we have to answer this question here, what are vectors? We would have to say a vector is two pieces of information. Two pieces of information. A, it has size, and B, it has direction. Just like each of these forces did. Some of them point that way, small and big. That's what a vector is. Now, besides knowing what a vector is, you'd probably want to know, well, how do we describe them? To describe them, we will take two usual approaches. How to describe. We will either draw a picture, or B, we will use ordered pairs. Okay, we will describe these vectors in one of these two ways. Let's have a couple examples. This vector, the order pair could be maybe 5, 1. And we note these pointy brackets this way because we want to distinguish it. It's not, if we had the round brackets, it would seem like it's a point, and we don't want to say point. When we want to say vector, we use these pointy brackets. The picture of that vector, say we call it V. That's another thing that you got to note. Whenever we're talking about vectors, it is often the case that we will denote them with either bold-face V or a little arrow on top to say, hey, that's not just a regular point, it's actually a vector. That's the algebraic way of showing it. The picture would look something like this. You would start at any given position, and you'd go 1, 2, 3, 4, 5 units, and you would go up 1. And that right there, that's a picture of V, the same vector we've got up there. Notice if somebody else draws the vector somewhere here, so long as they draw the same direction, same magnitude, that is 1, 2, 3, 4, 5 to the right, 1 up, even though they're positioned differently, this one's on top of this one, they are still the same vector. Okay? That's what a vector is. Okay, now what we want to do is, we want to put this on pause and then proceed as follows. Now, what I want to do is learn how to add these vectors. we'll take two different looks at them. First look, just using pictures. Suppose you have the vector that looks like this, and we'll call this vector v. Suppose you want to add it to a vector that looks like this. We'll call this vector w. How do you add those just using the pictures? Well, you kind of have to imagine you've got a force acting this way in that size, and you've got another force acting this way of that size. Altogether, what sort of force do you have? Well, famous technique is the definition of adding vectors. You take this vector, draw it again, exactly the same size, same direction, and you take this one, but this time place it tip to tail. Wherever V ends, W starts. So it looks kind of like this. This will be W, same size, same direction, same direction. What you get out of that would be a vector like this. This vector is what we call the vector V plus W. The sum of two vectors gives you another vector. It's called the resultant vector. Sometimes the resultant or the resultant force, depending on what you're dealing with. That's how you add vectors. Picture-wise, you just use tip to tail. And you may ask, well, how do you do it without using the pictures, just using the algebra? Well, let's just put some numbers on this. Suppose this is 1, 2, 3, and up 1, 2, 3, 4. And suppose this one is 1, 2, 3, 4, and maybe up 2. So let's take a look at the same example, but this time using just the algebra. So what if you had to add 3, 4, that's V, plus 4, 2, that's W. The result would be you would add the corresponding x's together. You went 3 that way, and you also went 4 that way, so you went a total of 7 to the right. You went 4 up and 2 up, so a total of 6. That would be the resultant vector. And incidentally, you should be able to check that. It should match with the picture. If you go over 7, 1, 2, 3, 4, 5, 6, 7, and you go up 6, 1, 2, 3, 4, 5, 6. Well, maybe my picture is not perfect, but you get the point. The picture should match the algebra here. Two different ways of adding vectors, using pictures, tip to tail, or using the actual sums. Okay, let's pause this for a second and come back and do some subtraction. Okay, let's take a look at the subtraction problem. Suppose you've got a couple of vectors here. V, which looks like that, and W, which looks like that. We're going to subtract it two different ways. First, just using the pictures, and then we will subtract using the algebra. Famous technique here for subtracting is to look at this following arrangement of the vectors. Suppose you place the vector V this way. Notice it's same size, same direction. And you place this vector here, but not the way you added, not tip to tail, but tail to tail. So you would place it more or less like this. There's your W. Same size as W, same size as W, same direction. The trick here is to take a look at this vector here that unites the tips. Suppose we call this vector X, the vector X. Now, take a look at this arrangement. If you make X point that way, then X and V are tip to tail. So that you can say that W plus X is equal to V. Just from this picture. W, tip to tail, X is the same thing as V. Now, if you write it that way, that would tell you that X would be equal to, by subtracting W from both sides, V minus W. There you go. What you've done is you found out what the vector is from V, or V minus W. It's exactly this vector, X. This is called tail to tail, to subtract the vectors. It's not the only way to do it, just one way to do it. Take a look at the same problem algebraically. Suppose this is over 3 spots and up, I don't know, 5. So this would be 3, 5 minus, suppose this one is over 4 and down 4. So this would be 4, negative 4. The way you subtract would be exactly as you would expect component-wise. You got 3, take away 4, that gives you negative 1. 5, take away negative 4, which means 5 add 4, that gives you a total of 9. This would be exactly the same problem done algebraically. And note that it should coincide with the picture. If you go left 1 and up 9, it is exactly the same thing as x. Left 1 over up 9. Okay, nice. Two different ways to see subtraction of vectors, algebraically or tail to tail. Okay, let's put this on pause for a second. Okay, for the scalar of a vector, again we'll do two different ways, using the pictures and then using the algebra. Let's take a look at the picture here. Suppose you got a vector w here. What happens when you add the w to itself? Well, you'd have another copy of w just like this, tip to tail. The whole vector, from beginning to end, this vector right here is what we would call 2w. So we call this number right here a scalar because it scaled the w by 2, or in other words, it multiplied it by 2. Contains the same direction in this case, except it's twice as long. By the same token, you could have a case where you have w in this direction, for example. And what would happen if you took your w and you just contained the same direction but just went halfways? Well, we would call that half w. And we say this is a scalar, and we say that w is scaled by half. Okay. The other thing to look out for is, suppose you have w here, w. What would happen if you take your same w, same direction, except you switch it by 180 degrees? Exactly the same size, you just switch the arrow going the other way. We call that negative w1. In some sense, it's a scalar. So the scalar here is negative 1. And when you have the scalar is positive, you just change the sign. When the scalar changes the sign, you also change the direction. When the scalar is negative, that is, you would change the direction of the vector to the opposite direction. That's using the pictures, and maybe we can do just a little bit of algebra here. Suppose w is equal to 3, negative 4. Well, twice w would be equal to exactly what you would expect it to be. Twice 3, negative 4, and then you would distribute that 2 in there. That would give you a total of 6, negative 8. Similarly here, if you wanted to find for the same w, a half of w would be a half 3, negative 4. You would just distribute that. That would give you 3 over 2, negative 4 over 2, which you could simplify if you want. That right there would be called half w. And similarly in this case, if your w is equal to 3, negative 4, negative w would be negative this, and you would distribute this negative and that would give you negative 4, positive, negative 3, positive 4. That's 3 different examples using the pictures, using the algebra. This is called scalars, or scaling a vector. Okay, let's put this on pause and see what other good things we got going on today. Okay, now let's take a look at this question of magnitude of a vector. The magnitude of a vector is really just the size. In plain language, it's just the size of the hypotenuse for this triangle that the vector makes. So to find that should be an easy problem if you've been paying attention in the course. We've had the very, very famous Pythagoras theorem that says if this side is 3 and this side is 5, then the size of this guy, we'll call it x, would be given by the following relationship. 3 square plus 5 square is equal to x square. That would tell you that 9 plus 25 is equal to x square, which would tell you that 34 is equal to x square, which would tell you that x equals plus or minus the square root of 34. You could just, if you're just looking at the size, you may interpret that as just a positive number for now. That will give you the square root of 34. This size of v we denote by the following symbol. We use this sort of absolute value v, and we all know when people write that we mean, we all mean the same thing. We mean the size or the magnitude of v. So in this case, the size would be square root of 34. That's how you get the magnitude in general. You're just using Pythagoras here. Maybe we can follow that with another quick example. Suppose you have this vector here, which is w, and suppose it's given by 10 and 5. Okay, the norm of w would be given by 10 squared plus 5 squared, and then I would take the square root. So it would be the square root of 125, or the square root of 125. That's the norm. Okay, or magnitude. This is actually a good time to review another really important concept. What would happen, or it is often desirable to look at vectors that have size 1. For example, 3 over 5, 4 over 5. This vector, which is really sort of a small vector, in the right direction, you don't even go one whole unit. You simply go 3/5 of a unit, and you go up 4/5 of a unit. So this vector right here, you go 3/4 to the right and 3/5 to the right and 4/5 up. The question is, what's its magnitude? Let's check. Its magnitude would be the square root of 3/5 squared plus 4/5 squared. That would be the square root of 9 over 25 plus 16 over 25. And what is that equal to? Well, that would be the square root of 25 over 25. That would be the square root of 1, which is equal to 1. Whoa. We just showed that this vector has size 1. This guy is exactly 1 unit. When that happens, we have a very, very special occasion. We call this a normal vector, or normalized vector, however you want to call it. Meaning that it's a unit, or sometimes people call it a unit vector. All these things are the same. Unit vector, normalized vector, they're all the same. They're telling you that the size is exactly 1. More than that, what we want to do is, suppose somebody gives you one that's not size 1. Suppose they give you one that's size 3 over and 5 or 4 up, and this is your vector v, which is equal to 3, 4, just like that. One of the important skills that we need to know is how do you normalize v, meaning I want a vector just like v, but much shorter. I only want it to be length 1. This would be a little tiny v, or a standard size 1 v, unit v. Well, really, people call it the normal vector for v. That's that guy right there. And the question is, how do you get it? Well, it's just this one scaled. Here's what you do. In general, to get this one, all you do is take your v and multiply by this scalar 1 over its magnitude, just like that. And that will always give you the normalized vector. Let's try it in this case. First, we find the norm of v. How big is it? To do that, we do the square root of 3 squared, which is 9, plus 4 squared, which is 16. So it's the square root of 25, which is equal to 5. Then we just follow this procedure. It's 1/5 times 3, 4. And the way we scale it would be 1/5 times 3, that would give you 3/5, and 1/5 times 4, that would give you 4/5. Now this little tiny vector is exactly that one. It contains exactly the same direction as v, but size exactly 1. That's what we call normalizing a vector. It will always be well, except for 0. 0 is the only one you can't normalize. It will always be obtained from here, taking v and divided by the size of v. Okay, let's. So that's this discussion on size or norm, and that's the discussion on unit vectors or how to normalize a vector. Let's see, what else have we got here?